Hi, everyone. Thanks for joining us. Today, we're going to have our session on lessons learned for a utility-owned thermal energy network in existing urban dense environments. Fantastic. Hi, I'm Charlie Marino. I'm with WSP and our Built Ecology team. I focus on building decarbonization and thermal energy networks in the existing building space. I'll ask my fellow presenters, Adam and Brittany, to introduce themselves. Brittany?
Hi, everyone. My name is Brittany Preventer. I'm an engineering manager on Con Edison's utility-owned thermal energy network team, and I technically manage our two Manhattan UTEN pilot projects.
Hi, I'm Adam Shelley with Ecosystem Energy. I'm a director of innovation and project development, and we're the program lead on this project with Con Ed and WSP.
Great. So Brittany will get us our conversation started with a quick overview of the Utility Thermal Energy Networks and Job Act.
Okay, so the reason why we're talking to you today is because of a law that was passed in New York in 2022 called the Utility Thermal Energy Networks and Job Act, or UTENJA for short. So it allows utilities to own and operate and maintain thermal energy networks in their service territories. The law also required the 7 biggest utilities in the state to design and propose at least one thermal energy network pilot project to the New York State Public Service Commission, our regulators. The law was passed for a variety of reasons shown on the slide, like testing if a utility-owned thermal energy network, or UTEN for short, can meaningfully contribute to the state's electrification goals by reducing building emissions. As a result of UTENJA, a UTEN team was formed at Con Edison. I was hired, and the team proposed 3 UTEN pilot projects to our regulators. We're more than halfway finished with designing all 3 pilot projects and figured we'd use this opportunity to talk about some of the lessons learned we'd encountered during the design of our 2 Manhattan pilot projects, Chelsea and Rockefeller Center. But before we start to talk about lessons learned, what is a UTEN? So a UTEN is a district energy system, but one that's owned and operated by a utility. Most of the time, district energy systems go hand in hand with geothermal applications. However, installing boreholes in a large, dense city like New York City can be a challenge. UTENs can use other heat sources and sinks than geothermal boreholes, like waste heat captured in condenser water and chilled water plants. So like I mentioned before, you'd think that implementing a UTEN in a large density like New York City would be challenging. However, a study we performed shortly after UTENJA was passed shows that UTEN potential is location dependent and that Manhattan is an attractive location for UTENs. Good candidates for UTENs have plenty of thermal resource availability. Large cities like New York have many thermal resources available, like sewage plants, waste heat recovery from subways, data centers, and condensate recovery if the city has a steam system like Con Ed does. Good candidates for UTENs also have building low density and are easily compatible with buildings' existing HVAC systems. Low density means less pipe to run for a more cost-effective project, and building compatibility is also important for minimizing overall project costs by limiting how much it'll cost to retrofit an existing building to be able to connect to a UTEN. As a result of UTENJA, Con Ed is creating a new thermal commodity. We hired multiple companies and regularly engage with the project stakeholders in order to design safe, reliable, and efficient UTEN pilot projects within a short time frame. Ecosystem and WSP are designing both of Con Ed's Manhattan UTEN pilot projects. We also hired 2 peer reviewers, KWL and RCM, to ensure that the designs are reviewed by industry experts before they're submitted to our regulators for approval. So the first of our 2 Manhattan pilot projects is in Chelsea. Our Chelsea project captures waste heat from a commercial office building with a data center in it located at 85 10th Avenue. We tap into the condenser water return in the building's chilled water plant to provide heat to the UTEN, and we'd use the building's cooling towers if we need to reject any heat from the system. The UTEN would supply domestic hot water to 3 large multifamily buildings located at the New York City Housing Authority's Fulton Houses campus, which are located about a block east along West 16th Street from 85 10th Avenue. Domestic hot water would be generated by using CO2 water source heat pumps in the cellar of each building. And the UTEN would also provide space heating and cooling to one of the NYCHA buildings by using a water source heat pump and a fan coil unit system. So the second of our 2 Manhattan pilot projects is in Rockefeller Center. Con Ed's Rock Center project captures heat from a large interconnected campus of buildings in Rock Center and distributes it to 3 nearby large commercial office buildings. Like Chelsea, will capture waste heat from the condenser water return in a large central chilled water plant. However, the waste heat captured in the central plant comes from many sources throughout the Rock Center campus, such as an ice plant and exhaust heat recovery coils. The 3 buildings shown on this slide will use large-scale water source heat pumps to convert a portion of their heating systems from steam to the UTEN. So New York State implemented a phased approach to each utility's UTEN pilot projects. Con Ed's currently in stage 2 for each project, which is the engineering design phase. By the end of stage 2, Con Ed will have construction-ready drawings, packages. We're aiming to file each project with our regulators in July of this year. After a few months, we'll learn which of our projects will be approved by our regulators to head into the construction stage, which is stage 3. We think it'll take about a year and a half to construct each project. So since the pilots will run for at least 5 years, we think the pilots will be in operation from the beginning of 2028 through at least 2032. Now, while we design these projects, Con Ed has several priorities in mind from a utility perspective. One of our biggest priorities is to generate as many learnings as we can for both Con Ed and the state. How easy will it be to retrofit existing buildings so they can connect to UTENs? Will UTENs help provide a more cost-effective way to help the state electrify? We won't have the answers to these questions until we finish designing and constructing these projects. Since we're a utility, we also need to make sure that there are several levels of redundancy built into the design to provide reliable service to our customers, like an N+1 pump redundancy and having a dedicated steam service to provide emergency heating if there's an issue with the primary thermal resource for our projects. These projects will also need to be scalable so the UTENs have the ability to expand in the future to include additional customers and thermal resource providers, since we're building a brand new commodity. We're also focusing on things we need to do to create the new commodity, like choosing reliable BTU meters for billing and creating customer protection plans. Other than utility priorities, there are other factors that influence design decisions, like space constraints. In a big city, space is at a premium. It would have been nice to build a new building to house utility UTEN equipment in Chelsea, but we couldn't build a new building on existing green space, and it would have required a zoning override by the mayor if we eliminated parking spaces to build a new building. For Rock Center, it's been tricky to find enough room to place equipment in due to already crowded MERs. We also had to think about compatibility with existing infrastructure. For the Rock Center project, since the perimeter induction unit loads for all 3 buildings already use hydronic heating, those loads were targeted to be converted from steam to the UTEN. Energy resilience and redundancy planning are also crucial to ensure reliable service to our customers. One design decision made to ensure reliable service was to leave the existing radiators in place in the Chelsea customer building so they could be used for heating if the UTEN fails. Regulatory and permitting challenges also affected design, particularly the New York City Department of Transportation permits, but Adam will talk about that a little later. I'll now pass the presentation over to Charlie to start talking more in depth about the lessons learned we've gathered while designing these projects.
Thank you, Brittany. Like any other project, we have experienced a number of lessons learned throughout this process. A number of those are related to the complexity of trying to enable a UTEN in an urban dense environment. And so we've listed a number of those key lessons learned here. The UTEN system strategies, which I'll talk about in just a moment. Adam will talk us through both test pit coordination findings, as well as how best to coordinate through multiple different stakeholders and somewhat like an arranged marriage. Several other lessons learned that we thought made sense to highlight as part of this conversation. are related to some of which Brittany has already mentioned. Coordinating space for new MERs, thinking about the right way how to plan for future expansion, and lastly, and importantly, emergency operation considerations. So I'll move forward with lesson learned number 1 there, UTEN system strategies development. So one of the key components for this overall project was making a determination of whether or not we wanted to utilize an ambient loop, which utilizes heat recovered from the condenser water loop and distributes that via heat exchangers to another set of heat exchangers to present heat for heat pumps that would be reliant on the customer side. And I'll discuss this in a little bit more detail in just a moment. The other approach was utilizing a low temp hot water system. And that's more tried and true in terms of these campus distribution energy networks, in terms of trying to utilize heat recovery chillers to generate low temp hot water, and then utilizing that through a heat exchanger that would serve individual customer buildings. And so we had to compare the two to try to understand which was the best approach among a couple different conversations. You can see here, we will highlight some of the key comparisons that we drew to get all the stakeholders involved and make a determination of which way we wanted to proceed with. Of course, the design temperature of what the actual UDS, the utility distribution system, would be in between the thermal resources and the individual customer buildings was pretty key. But also giving some thought to what was the limiting factors of generating heat within 30 Rock, our central plant, and our energy center. That turned to be the number one key decision making in this overall process. Whereas if we were to generate low temp hot water at 125, which was more advantageous for the customer side, we'd be limited with overall capacity for not just the stage 1 pilot phase, but potentially expanding future in years to come. Additionally, we gave some thought in terms of what would the pipe sizes be. For this particular pilot, we have sized the customer UDS that's related to the overall heat pumps that will be at their particular sites. And the ambient loop requires 2 separate pairs, which I'll show in just in the diagram in a moment. So there was some areas where we thought the low temp hot water would make more sense based on pop size and constraints that we see in the individual street. On the next slide, we discuss a few more of these design considerations, giving some thought about since we're utilizing both existing buildings and systems to recover heat from on the thermal resource side, and we have existing customers with their infrastructure, understanding the operational issues is also a key component in trying to limit major changes in that type of process for both buildings was really important to us. So we took that into account, as well as how it would impact their day-to-day operation. And understanding both of those, with lastly thinking about controls, is really where we made our final determinations. As you can see on the bottom there, our overall UTEN system controls for ambient loop will be a bit more complicated because of the kind of the scenario between the different heat exchangers and its correlation to an existing system that's generating heat based off a condenser water loop. But we feel as though the ambient loop made the most sense at the end of the day, again, because of the overall capacity that was available for our system. And the next slide here, you'll see overall diagram of what's actually happening with the UTEN system. And so the building 1-9 cooling towers, which are located at 30 Rock in Rockefeller Center, are generating heat, are displacing heat from the existing chillers. And so we're tapping into that condenser water loop and grabbing that heat directly from the chiller. And now once we get that into our heat exchanger and we displace it into the utility distribution system, we're able to pass that off to the other individual buildings through a series of other heat exchangers and hydronic loops. As you can see at the top of the diagram, we also have consideration for futures, where we're hoping to expand to some of the neighboring buildings along Avenue of the Americas. I'll pass it off to Adam to go over lesson learned number 2.
So lesson learned number 2, test pits. Remember, we're in Manhattan in New York, and I'll be happy to report that it is just as complicated to bury a new distribution system underground as we thought it would. So what you're seeing on the screen here is the number of paths that we identified. Try to be as open to as many different approaches as possible before you start the test pits, because you have to adapt depending on what you find under there, including the paths not imagined. Each one of the colors, the cyan, the red, and the yellow, and the magenta, are its own imagined pathways that we were hoping could be successful. And the red boxes are the test pits themselves that we've identified. If you're familiar with New York and the Rockefeller complex with the Christmas tree, this is adjacent to that. And it is a very busy avenue with cars and trucks on top, and it's very crowded below. So it's planning for that and anticipating that as much as possible and trying to learn as much as you can about what's underneath that entire avenue in as few test pits as possible for budget and impact reasons, but enough so that you're able to accurately gauge what's there and what you're going to run into when you build this multi-million-dollar piping network underground. So I cannot stress enough, if you're in a dense urban environment, check to see if there's any construction embargoes as well. For example, holidays, elections, UN meetings, or anything else that might disrupt this. You cannot plan far enough in advance in order to accommodate those into your schedule. Taking all this into consideration, it's really important not to lock any one part of your design in where something has to be done in a certain way, because you really don't know what you're going to find under there. On the next slide, you'll see these are a couple of pictures of the test pits by Rockefeller Center. Most of what we found was anticipated. The drawings were pretty good and complete. There were a few shifts which are modifying our design, but nothing that we found yet that we can't get around. And the picture on the left is just a really beautiful picture of one of our partner buildings and the construction going on in front of them in the middle of the night. It sort of looks like Gotham City in that picture. We think it's pretty cool, but it's fun to be out there. But you cannot, there's no way to plan more in advance than you need to. The next one, those are the test pits, both at Chelsea and Rockefeller Center. Overall, we learned something very early on, that the success of this project was going to depend on the stakeholders involved in this and what we're calling our arranged marriages between the three of our groups at Con Ed, WSP, and Ecosystem. The structured agreements and the incentives and the type of relationships that we've had are helping to drive the success of this project in the limited amount of time that we have to complete the full design, which is about 9 to 12 months. Technically, Ecosystem is subcontracted to Con Ed, and WSP is subcontracted to us. But really, WSP and Ecosystem are partners in this in terms of operations, and that was identified very early on, even before the project went to RFP. So we thought that was critical because WSP and Ecosystem fully understand the scope of the project, the goals, what the outcomes should be, and we share that risk between us. We thought that was really important day one to have a turnkey contract, which is what Con Ed really wanted. As a utility, a regulated utility that's sometimes risk adverse, it was very important for them to shift off as much risk as possible to us. And so in order to do that, the contract had to be very thorough, very specific, and transfer as much of that risk onto the rest of the team as possible. We also identified collaboratively the needs for contingency and just general levers to pull along this process in order to meet schedule and scope, because we didn't know how this was going to work out. It's a very integrative, collaborative, thorough design that touches a lot of different places in New York City, as you'll see in the next slide. But in order to meet that, we needed to have as many levers and contingency to pull as needed. A few other comments. Our relationship with our civil site contractor is almost the complete opposite as it is from WSP, in the sense that it was not a turnkey contract. There was a base scope of work, but there was a lot of scope that was identified as potential depending on what we found underground and what the needs of the projects were as development occurred. Wrapping all of that up in a very productive, integrative form of communication and trust building along the way, we think was critical. And that we've been working the design on this project for, I think, about 3 or 4 months. But in reality, we've been working together to develop the project to get to design for over a year and a half. And the reason that that time was so critical is because we were able to form a number of different connections within each of our organizations and build out the communication structure in which we could best respond to each other and challenge each other and advance the design and deal with any issues that we have, because obviously those were inevitable. Meetings, different reviews, some happy hours, some breakfasts, lunches. We really threw everything as possible as we could to solidify our relationships because we knew that this was going to be a sprint on a very complicated project. So this has been extremely successful to date, and I think is one of the keys of success to this project. What you're seeing on screen is a very, it's obviously it's an org chart, but it's showing the UTEN end users on the top right for Rockefeller and Chelsea. Con Ed is on the left. We formed 4 key working groups, which aren't necessarily fixed working groups. They're there just to help the communication and facilitation around a number of different concepts, because it's not just about the design for Con Ed. It's also about the customer protection plans and the cost recovery mechanisms and tariffs and KPIs that the state put on them, as well as all of the different subs that are involved in making this project happen. The other part of the stakeholders on the next slide is just the additional stakeholders that are required to get this done in this neighborhood, as I'm sure is the case in many different urban areas. That's a picture of alphabet soup, because basically any acronym that you can come up with that you've heard of had to be involved at some point in this project. The 8 that are listed are probably the key players that we've had to coordinate and collaborate with, but there's been many others. The unanticipated stakeholders that have popped up on this project have been significant, and sometimes because this is a public process, there's been some harsh public comments with people not knowing any or all of the facts of these projects. And so the lesson learned here is to get ahead of that as much as possible. And this collective team set out to do that, and we did a pretty good job of that, but it needed to be more. So Con Ed pretty quickly implemented a strategic engagement team that was mobilized early on to get ahead of those concerns and work with people on an individual and corporate basis. The future. So what does this mean in the future? Where are we going from here? We're taking all of these lessons learned, and the expectation is to expand and add new thermal energy networks. If you go to the next slide, Brittany. So please, sir, may I have some more? Famous Oliver Twist line. Still, it applies many places in culture today, including NYC thermal energy networks. So hopefully these pilot projects go well. These will get expanded under Con Ed, but as Brittany showed in that map earlier, there are many places in New York where new thermal energy networks can advance either through private development or under Con Ed, and we're hoping to leverage these lessons learned to have additional successful projects in the future. So thank you all for your time. We look forward to seeing you in Boston, whether you're watching this before or after. Feel free to reach out to any of us. I don't know if Brittany and Charlie, you want to come back on the video. Any last words?
Thanks for watching. We look forward to talking more about our UTEN pilot projects in Boston. We'll talk to you then.
Yes. Take care.